Hi, everybody. So this week, your lab is very simple. You're going to be looking at a bunch of models and telling me the electron domains and the molecular geometry. There's a ton of questions. It's very theory intensive, so I'm going to do my best to help you on this video. So Lewis structures, that in your pre-lab, so I'm not going to go over this, but make sure you understand how to draw Lewis structures, because you have to do that for every single question. Resonance structures, I'll go over a little bit. And then we have VSEPR theory. So VSEPR theory is the idea that the shape and bond angles of a molecule are dictated by the number of electron-dense areas. An electron-dense area is defined as a lone pair or a single, double, or triple bond. It doesn't matter if it's a single, double, or triple bond. Each one counts as just one electron-dense area. So to start off, they've left off having just one electron-dense area, which only exists for the diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine. But those all have a linear shape, just like things that have two electron-dense areas. Things that have two electron-dense areas, so two bonds, have a linear shape. Three have a trigonal planar shape, and then fourth tetrahedral, and so on and so on. So you have two properties here. You have electron domain geometry, which is only dependent on the number of electron dense areas. So if it has two, linear; three, trigonal planar; four, tetrahedral; so on, so on. Molecular geometry starts off the exact same as electron domain geometry. You'll notice here, if none of the electron dense areas are lone pairs, then they have the exact same shape as the electron domain geometry. But let's say, for instance, in your thing that has three electron dense areas, let's say it has two bonds and a lone pair. This takes on a bench shape as opposed to a trigonal planar shape. For tetrahedral, it goes from tetrahedral shape to trigonal pyramidal shape. And then if it has another one, if it has two lone pairs, it takes on a bench shape. This is like water right here. Something to note is that as you add lone pairs, your bond angles change. So just for your base geometries, you have these right here, where linear is 180, trigonal planar 120, tetrahedral is 109. For trigonal pyramidal, you have two bond angles because you have two regions. You have an equatorial axis, which is to say it's flat like the equator. So there's three in the equatorial axis right here, and each of these has a 120 angle between each other. And then you have the axial axis, which are the things that go straight up and down. So these two are the axial molecules, or the axial atoms, and the axial atoms have 90-degree angles relative to the equatorial atoms. In octahedral, all of them have 90-degree angles between each other, even the axial and the equatorial. But let's say, for instance, one of these bonds becomes a lone pair. These lone pairs repel more than a bond does. So it actually causes these molecules to get closer together, making this less than 120. Same thing for tetrahedral. You take this and turn it into a lone pair. It goes from 109 to slightly less than 109, typically assumed to be 107. And then if you take even another bond and turn it into a lone pair, it gets even smaller, generally believed to be about 105. So keep that in mind, that lone pairs cause your bond angles to shrink from the default. So that covers what I want to talk about at VSEPR. Let's talk about your questions. For the first station, you have diatomics here. So these are all going to have linear shapes because they are just bound to each other. There's only one electron dense region. And it asks you to compare and contrast the number of bonds and bond energies of these molecules. It won't give you the hydrogen energy, but it's 432 kilojoules per mole. And then let's go back here. You have given bond energies right here. So we have oxygen with a double bond right here. So not a single bond, it is double bonded, gives you 495 kilojoules per mole. And then nitrogen is a triple bond right here. So it's not a double bond. It's not a single bond. It's a triple bond. It has this much energy. So you need to relate how the number of bonds affects the energy. For station 2, you are going to have two molecules here, and they're going to have double bonds and triple bonds present. So you need to notice how multiple bonds affect the shape of the molecule. And shape can mean either the size of it, the size of the bonds, or the size of the molecule, or the size of the angles if it has angles. So tell me how multiple bonds affect that shape. And then tell me how your Lewis structures have features that are not present in the molecular models. Because there are certain things that are present in Lewis structures that are not present in your molecular models. So pay attention to that. For station 3, you're going to build water with a black central atom and a red central atom. And a red central atom represents oxygen. and a black central atom represents carbon. So talk about how using a different central atom affects where your lone pairs are, and then do this for ammonia as well. And then compare each model with the correct central atom and talk about what you think the bond angles will be and why you think the bond angles will be that. For station 4, you're going to be moving on to resonance things. So resonance is this idea that electrons can be delocalized if there is no preferable position. So look right here. Why is there a double bond here but not here? You have the exact same two molecules that have a bond. And the reason why is because this bond is not right here. It can actually also be right here. You can take this electron right here, make a double bond here, and then this sulfur doesn't want to have 5 electron domain dense regions right now. It will push these up here. And so this is resonance. While you may think these are the exact same structures, these are two completely separate oxygen atoms. So it's a little bit different. But the sulfur dioxide atom does not, the sulfur dioxide molecule does not look like either of these. In fact, it's a mixture of the two, which is best represented right here. These two bonds are neither single or double bonds. They fall somewhere between. So you'll have to do that for this one, and you'll also have to do that for your other molecule here. So tell me all the resonance structures. Then there's going to be a pre-made molecule in front of you that has the correct bond angle. And it's also going to have different bond lengths. Keep in mind what I talked about it having somewhere between a 1 and 2, a single bond and double bond length. So make observations about the difference in bond angles and bond lengths. Then it asks you how you can best reproduce that 3D printed molecule using your set. So you'll have to use your set to do that question. And then finally, it tells you the name, the hybridization. When it says hybridization, it wants to know which of these shapes right here best describes it. Which of these? So which molecular geometry? Finally, we're going to move on to acetic acid. So it's going to ask you to identify the central atom of each atom in these molecules. So how you do that is you write out your molecule. So first thing we're going to look at is the CH3. And we're going to try and identify the molecule that is the atom that is the least electronegative that is not hydrogen. There's only one option here, which is carbon. So we're going to draw this right here with carbon in the center. There's the least electronegative atom goes in the center. And then we're going to move on. We have a carbon bound to an oxygen in the previous carbon. This carbon can't be a central atom twice, so we have to determine which of these 3 atoms is the least electronegative, and it's carbon. So this is going to be your second central atom. And then we move on to our oxygen here. This oxygen is bound to carbon, 2 electron dense regions, and a hydrogen. So carbon can't be the central atom again, so this oxygen becomes a third central atom. So that you have this central atom, this central atom, and this central atom. So you have to do that for acetic acid here, and then if it's possible, you'll have to do it for carbonate as well. Then you need to list all the polar bonds in these molecules. You draw polar bonds like this, where the positive side has this little plus sign at the end. You have a plus for positive, and you draw the arrow pointing towards the region that it has more negativity. So on water, you would draw one here and draw one here because the oxygen hydrogen bonds are polar, and the oxygen is what is pulling in the negative charge. So identify the polarity and then draw the arrows like that, and that's how you do questions 1 and 2. And then discuss whether the whole molecule is polar or not. Sometimes polar bonds can cancel each other out. You may particularly notice this in carbonate. You have an even geometry and you have the exact same 3 types of bonds here. So your polar bonds may just cancel out to have no net polar bond, polar like charge for the entire molecule. And then again, determine hybridization. That is just based off of molecular geometry. Tell me which one of these it fits. Moving on to station 6, we have an anomaly. BCl3, boron only has 3 valence electrons, so this is actually only going to make 3 bonds. You're probably thinking, this doesn't follow the octet rule. Well, the octet rule isn't always true. It's a lot better for molecules that are, if I could find my periodic table, it's a lot better for just these 4 or really these three right here. But boron can only make 3 bonds. As a rule of thumb, you can make as many bonds as you have valence electrons, and boron only has 3. So as a result, it is unable to make more than 3. So you're only going to have 3 bonds present here. Phosphorus, on the other hand, has 5 valence electrons and only has 3 bonds. So do you think this is going to have a lone pair of electrons as well? So keep that in mind. So compare the two molecules and talk about molecular shapes. Why are they different? Then does it matter where you place your lone pair? So does it matter if this lone pair is placed here or can be placed in between these 2 chlorines or these 2 chlorines? Does it really matter where they go? And then finally, determine hybridization again. Station 7, we're going to have the opposite problem. You're going to notice here that, for instance, this molecule right here, phosphor pentafluoride, has 5 bonds, which again breaks the octet rules. And the whole idea is that anything that has an empty 3d or just d orbital in general, which is everything that's over here and down, can actually break the octet rule. The octet rule is more of a guideline than an actual rule. And so it's actually possible to make as many bonds as it has valence electrons. Phosphorus has 5 valence electrons and it has an empty 3d orbital, so therefore it can make up to 5 bonds here. Sulfur, you're going to see later, can make up to 6 bonds. So keep that in mind that that can occur. So here is asking, is it possible to use the same central atom for all these molecules? So I want to point out that phosphorus has 5 valence electrons. So let's say you use phosphorus and make it phosphorus 4F right here. That means 4 electrons will be contributing to bonds, and it only has 1 electron. Is that possible? Can a electron exist by itself, not in a pair? And that will answer that question. And 2, it's asking you to compare the difference in bond angles. You'll use this to help you with that. And then to explain where the lone pairs are going to be. So you have molecules here that are going to have up to 5 electron dense regions. So are the lone pairs going to be equatorial or axial? This graph kind of gives it away. And tell me why that occurs, though. Why is it that we want to take from the equatorial position right here? And finally, we have our last set of questions. And these have 6 electron dense regions. I know, crazy. Compare the 2 molecules and discuss the differences in geometries and polarities. It's actually a pretty simple one. It's just both of these are going to have 6 electron dense regions. And finally, we have the big dog questions. These are the ones that are worth the most points, so make sure to answer these 4 questions. So first, list all the resonance structures and explain what resonance is. We've kind of talked about resonance already. It's that idea of delocalization of electrons. So list the structures that have resonance and explain what resonance is. 2, find the molecules that have a lone pair of electrons on the central atom, but is overall nonpolar. I'll give you a hint. There's only one, and it's going to be something that has a geometry that's very even. So look for that. There is one, I promise. 3, for each of the molecules in 2, which 2 is referring to this question right here, so the one you just answered, talk about why it doesn't have a net dipole. And then finally 4, why do we use model kits and what are the limitation of model kits? You should notice them as you do it. There are just some things that aren't represented by model kits, but they're overall a net good. So lots of questions. So make sure that you understand all of them. I really recommend that you do this lab report in lab because you can finish it and you can ask for help as you do it.